Hi, this is Mike Collins with the last video showing you how you can use the output from the Microlab visual spectrometer and a digital camera and various tools on your PC to generate a Beer's Law plot from the photographs. This is actually a complete surprise to us, but it turns out to work pretty well. So what I've got over here is a spreadsheet that I've put together that will relate the amount of potassium permanganate added to a deionized water solution or deionized water sample in the vial in the spectrometer. What we're going to do is get the background intensity for the blank, the DI water, and we'll compare that to the sample intensity at one of the absorption peaks for different amounts of added potassium permanganate to generate a Beer's Law plot. Let's open the photograph, and to save time I've actually created this photograph as a composite of a series of pictures. So from the bottom to the top I have DI water, photograph of the spectrum of DI water with helium piped in by the fiber optic cable. This would be useful if you wanted to do a wavelength calibration. We're actually going to work just with pixels. We don't need to do the wavelength calibration, but in principle you could. And then we have a picture of the DI water spectrum. I then added 50 microliters with a little spin bar in there. You can see where the spin bar is blocking the slit, where you get a little opaque horizontal line. Spun it for a few seconds to homogenize the solution, and took another photograph, added 50 more microliters, 50 more, and 100 more to get a total of 250 microliters, taking a snapshot after each one. I then brought all of those pictures into the Microsoft Picture Manager and did the exact same cropping on all of them and overlaid them, and then saved them as one JPG file. Now you wouldn't have to do this if you were working on your own. You could actually take a bunch of pictures as long as you have the same camera settings and do the same cropping each time. You could work with each picture individually. So this is to save a little time for me here. So we're going to go back to image J and use the rectangle tool to grab a piece of that spectrum on the blank, and we're going to analyze that and do a plot profile. So here we have the background, deionized water, and all the other optics including the vial. So we have the intensity versus pixel distance, which is really versus color or wavelength. So you can set that over there. Now I'm going to move the rectangle up. We're going to try to find out where we should do the analysis, what pixel we should choose. So here we're going to analyze and do a plot profile. We can see we've got an absorption band somewhere in the vicinity of 300 pixels. So let's just pick 300 pixels. Why not? And at 300 pixels we have an intensity of 40.2 for our first solution, and at 300 pixels we have an intensity of 66.4 for our blank. So we're going to go here, we're going to put in 66.4, and what did I say? 300? 39.9, close enough. And we'll put the background in at 66.4 for all of these. And you can see now we're getting an absorbance reading. So let's get rid of that. We'll go back and move on up. Every time we do a plot profile, we'll go to the 300 pixels and pick an absorbance or an intensity. Analyze, plot profile, go to 300 pixels, and that's about as close as I'm going to get, 30.3. Minimize that. .3. And we'll go up to the 250 microliter spectrum and get a plot profile. Seven point seven. 7.7. Okay, excuse me. So here we have it. We have our calibration curve in terms of the microliters of potassium permanganate added to the vial from 0 to 250 microliters, and our absorbance at 300 pixels. And we get a calibration line with a correlation coefficient of 0.98. Pretty good. You could experiment with different pixel counts to see what gives you the best line, but this shows you how you can use digital cameras to photograph spectra with our visual spectrometer and get quantitative information. Thanks for watching.